Hi there, this is the Calculus Crash Course for AP Physics, and this is going to be part 1 of 3, and we are going to, in this section, talk about derivatives and differentiation. And before we can talk about what a derivative is, we have to talk about secant lines, which you may have talked about secant lines in other courses, maybe in geometry. But a secant line is a line that intersects a curve at 2 points. So if we think about our secant line for the function f of x, and I have the function f here drawn in blue, the secant line being defined on the interval from a to b. So on the interval from a to b, the closed interval. Then the 2 points that we know our secant line would pass through would be a comma f of a, so at the first endpoint, and then b comma f of b. And the secant line can intersect other points on the curve on that interval, but we're really looking at the endpoints of the interval as being those 2 points that define the secant line. And then if we wanted to find the slope of the secant line, we would just apply slope formula, which is, remember, change in y over change in x. So in this case, change in y would be f of b minus f of a, and change of x would be b minus a. So that would be the slope of this line. Now, another notation we could use is replacing a and b. So replacing a with x and replacing b with x plus h. So that means that the interval for our secant line would be the interval from x to x plus h. So this point, this first point, instead of being a comma f of a, would be x comma f of x. And then this second point would be x plus h comma f of x plus h. And then if we thought about applying slope formula using this notation, change in y would be f of x plus h minus f of x, over change in x would be x plus h. Here, I can write this out. We would have f of x plus h minus f of x for change in y over x plus h minus x. So if we're using this notation for slope of the secant line, notice that the x's will cancel every time. So then that's why we just have h in the denominator here for the change in x. Now, you may have seen this formula before. So we, again, just applied slope formula, change in y over change in x. But every function has a formula that you can use to calculate the slope of a secant line over an interval. Like this kind of gives us, instead of having actual set intervals, like from 2 to 5 or 7 to 9, we can think of any interval on the function as being x to x plus h. And then whenever you find f of x plus h minus f of x all over h for a given function, this is a formula that you could use to calculate the slope of the secant line. You would just have to plug in whatever x is, so the first value, the first endpoint on the interval. And then h, so if we look back at our picture here, h actually represents the length of the interval. So if you know the length of the interval, then you could plug in what h is. This is referred to as the difference quotient. And every function has its own difference quotient that you can use like a formula to calculate slope. Now, you already have slope formula. So like if you know the actual values, like the actual interval that you're calculating slope of a secant line for, you might as well just use slope formula. But the difference quotient is going to allow us to lead to a new definition. Okay. So this leads us to a tangent line. Now, a tangent line is a line that intersects a curve at exactly one point in the neighborhood of that point. So I have our function f, the same function as before drawn. And like this would be the tangent line to the curve f at x equals to a. So this would be the point a comma f of a. Now, if this line were to extend, especially like looking at the behavior of f, it looks like f probably continues up, up, up. So like if we were to think about extending this tangent line, it would eventually intersect f somewhere else, and that's okay. But we're looking at the tangent line as touching the curve at exactly one point in that neighborhood of that point. So in the neighborhood of x equals to a, this is the line touches at the point a comma f of a, and nowhere else. Now, the thing about a tangent line that's cool is if you were to zoom in, which the iPad is of course not going to let me zoom in very much. If you were to zoom in more, like Desmos would do a great job of this, it would look like the curve, so f, in the tangent line, were merging as one. Meaning the curve f we would refer to as being locally linear. Like it would almost look like f is a line, the more and more zoomed in you get. And because of that, the tangent line is going to tell us something interesting about the graph of f. Now, before we get into that, let's talk about how we would come up with the slope of the tangent line. And to do that, we need to go back to this previous picture and our difference quotient. So in this picture, if we thought, let me change this back here. If we thought about pooling this point at x plus h, comma f of x plus h towards the point x, comma f of x. So meaning making this interval smaller and smaller and smaller. So making this point move along the curve towards the point x, comma f of x, x, comma f of x. Then the slope of your secant line would become closer and closer and closer to the slope of your tangent line, right? Like if you thought, is this the pointer? I've never used it. So if you thought about moving this point along the curve and calculating the slope of the secant line at every single combination of points, so moving closer and closer and closer to x, comma f of x, as we get closer and closer in the neighborhood of x, then the slope of the secant line, so the slope of the line that passes through the endpoints of the interval, we would get closer and closer to the slope at the point x, comma f of x. And I hope with the language that I'm using, you're thinking, limits? Are we thinking limits? So in this case, of the point x plus h, comma f of x plus h, getting closer and closer and closer to x, comma f of x, h would be getting smaller and smaller and smaller, approaching 0. So the slope of the tangent line, I'm going to abbreviate M sub tan, would actually be the limit as h approaches 0 of the difference quotient. So of f of x plus h minus f of x all over h. Now notice that if you were to use direct substitution here, right? Remember direct substitution? So if you were to substitute 0 in for h, notice you'd end up with indeterminate form 0 over 0. So there's usually some algebra or eventually even calculus, which is funny because this whole definition is the basis of derivatives, right? Or that's what we're getting to. But you would have to do some work in order to get this h to cancel so that you could actually evaluate the limit analytically. But the slope of the tangent line, so this would be the slope of the tangent line to any point on the curve where the slope would exist, would be this limit. Now, why do we care about that? So the slope of the tangent line is the limit as the size of the interval over which the slope of the secant line is being calculated goes to 0 of the difference quotient, which is the formula for the slope of the secant line. We refer to the formula that results from the limit as the derivative of the function. So this matters because that limit, the slope of the tangent line, is the derivative. So the derivative can be used to calculate the slope of the tangent line to the curve. So where difference quotient is a formula for a function to calculate the slope of the secant line over an interval, the limit as h approaches 0 of the difference quotient is actually the formula for the slope of a tangent line to the curve. So at any point on the curve where the slope of the tangent line would exist. The notation for the derivative is this. Well, this is one of the notations. And we read that notation as f prime of x. So this is like the function notation for a derivative. And a derivative is a function, right? So a derivative would actually be a function. So it's a notation that indicates the relationship to another function. So like if you have the function f of x, its derivative would be f prime of x. Other notations that you should be aware of are dy over dx, that's this one. Dy over dx, or sometimes it's just read even dy dx. And then y prime. These are some other common notations. Now, another way to read dy over dx is the derivative of y with respect to x. Because the derivative is a formula that tells us how y is changing with respect to x at that point. X being the independent variable, y being the dependent variable. So dy over dx and y prime are usually used whenever you have a function that's in the form y equals. And then f prime is used when function notation is being used to represent a function. So like if you're trying to find the derivative of g of x, you would say g prime is the derivative. Now, why do we care about finding the slope of a secant line or a tangent line? That's a big question. Well, the slope of a secant line on an interval from A to B represents average rate of change of a function on that interval. Average rate of change. And the slope of a tangent line at a point would represent instantaneous rate of change. The example that I like to give for talking about average rate of change versus instantaneous rate of change is like, let's say that I'm going on a road trip. And I gave you the distance that I was traveling and how long it took me to get there. From that information, thinking about how long it took me to get there as being the interval of time, you could figure out on average how fast I was driving in my car. Right? Like if you said, if you knew the distance and how long it took me to get there, you could take that distance and divide it by the amount of time, and that would represent the average speed at which I was driving, right? In maybe miles per hour if the distance is given in miles, and then the time in hours. So, for example, if I told you I was drove 120 miles and it took me 2 hours, then you could say like, oh, well, on average, you were driving 60 miles per hour. Now, that doesn't mean that I was driving 60 miles per hour the entire 2 hours, right? Like I could have been driving at 65 miles per hour at some times, or like the open road, I could have even hit like 70, 75, 80. Or I could have been stopped. Like I could have had a pit stop on that drive. And that is where we get into thinking about instantaneous rate of change. So the rate of change at a specific moment in time. Like there could have been a moment in time where my instantaneous rate of change, the rate in that moment that I was driving, was 75 miles per hour. And that would be different from the average rate of change, which would be my change in distance over an interval of time instead of at a specific moment. We will get way more into that in our own class in AP Calculus AB. But just to give you a little bit of an understanding of the difference between slope of a secant line being average rate of change and slope of a tangent line being instantaneous rate of change. Okay? Difference quotient versus derivative. Now we have shortcuts that we can use in order to find the derivative of a given function. And you need to know all of these rules, all of these shortcuts. So the first one, and we're going to go through examples of each of these rules. So there's power rule. Very handy. Power rule is kind of the simplest rule. Product rule, because you're not allowed to just think about taking the derivative of each factor. If you have a function that you can think of as a product of two functions, you can't just take the derivative of each factor. It doesn't work out. So we have this rule. So derivative of the first factor times first factor times the derivative of the second factor plus the second factor times the derivative of the first. Now, product rule involves addition. So since addition is commutative, those products can be switched around. Like the order in which you think about taking like first factor times derivative of the second, that can be flip-flopped. Quotient rule, on the other hand, has subtraction in it, so it cannot. So quotient rule is if you're taking the derivative of a function that you can think of as a quotient, right, as a fraction. And to apply quotient rule, it's g of x times f prime of x minus f of x times g prime of x over g of x squared. And I have a little rhyme that I like to use for finding quotient rule or applying quotient rule. So instead of, in this notation here, all these notations, this says you're taking the derivative of whatever's inside the grouping symbol here with respect to x. Right? So derivative with respect to the independent variable. So this x, whatever this variable is, what was that? Whatever this variable is tells you what you're taking the derivative with respect to. Okay, so instead of writing f of x over g of x, I like to use high, low. Right? Like high, it's up high, low, even though I'm not spelling it like that, low. Okay? So the little rhyme that I use is low d high minus high d low all over low low. So low times d high minus high d low all over low low. If you look at it, right, here, low, d high means derivative of the numerator minus high, d low is derivative of the denominator all over low low. That's the denominator squared. So you can use that if it helps you. And then we have chain rule. So chain rule is whenever you have a function inside another function. So like f composed of g. And to find the derivative of a function that's a composite function, you think about taking the derivative of the outside function, so f prime, then you leave the inside alone, so g of x, and then you multiply by the derivative of the inside. I always say that to myself. Derivative of the outside, leave the inside alone, times the derivative of the inside. And then we are going to derive, in our class, we'll derive all of these derivatives of these transcendental functions. These are rules, facts. You just need to memorize and accept for now. So like the derivative of e to the x is e to the x. Derivative of natural log of x is 1 over x. Derivative of sine is cosine. Derivative of cosine is negative sine. And derivative of tangent is secant squared. So now we're going to work through each of these rules, some examples. So, to find dy over dx for y equals x cubed minus 3x squared plus 4x. This is a polynomial function. Each of the terms is just a variable raised to a power. So we are allowed to just apply power rule. And then kind of like with limits, remember a derivative is a limit, where you were able to think about evaluating if you had a function that you could think of as a sum or difference of terms and you were allowed to take the limit of each term. Same thing with derivatives. You can think about taking the derivative of each term in that function that you can think of as a sum or difference of other functions. So dy over dx will be equal to, applying power rule, to find the derivative of x cubed, we would bring the 3 down, times x and subtract 1 from the exponent, so 2. And then minus, the 3 is going to hang out there. Same thing like with limits. You can always think about pulling a constant out. So the 3 will hang out there, and then when we apply power rule, that will be bring the 2 down. X, subtract 1 from the exponent, will be 1. And then the 4 can hang out there. And applying the power rule for x, you would bring down a 1, and then when you subtract 1 from 1, you get 0. So this actually simplifies to just be 6x, or sorry, I was thinking about taking the derivative of that. 3x squared minus 6x, and then that's just plus 4. So the derivative of 4x is just 4 because the derivative of x would be 1. Okay, now, this is a function that's written as a quotient. You can either apply quotient rule, which we're going to do in a couple minutes, or this one you could just split up with algebra, right? Like this can be rewritten, let me go down, as 2x squared over x squared minus x over x squared plus 1 over x squared. Which if we simplify that, that's 2. And then that'll be minus 1 over x, which can also be written as x to the negative first. And then that's plus x to the negative second. And you'll find that a lot of functions, when you're trying to find the derivative, there's options on the order, on which rules you apply and the order, and or the order that you apply them in. So now to find f prime, we can just use power rule in the way that we have the function f of x written. Now the derivative of a constant will be 0. And if you think about 2 as being written 2 times x to the 0th power, well then 2 times 0 would be 0. Right? So then that's just 0. So f prime will be 2, and then multiply the negative 1 by negative 1. That'll be plus x, subtract 1 from the exponent, minus 2, and then minus 2x, subtract 1 from the exponent to the negative third. And then to write this without negative exponents, there we go, that's f prime. Okay, so that would be the derivative of that function. Okay, getting into product rule. And you can always pause this video and like try some practice problems on your own from what's assigned and then come back to the next rule if you want. Okay, so finding y prime. So notice this is a function times a function, right? A function created from thinking about having a function times another function. Now this could get multiplied out. Like you could easily multiply that out and just apply power rule, but we want to practice product rule. So y prime and showing your notation for the derivative is very important to show its relationship to the original function. Like so you know what that function represents. So applying product rule, I'm thinking of 3x plus 1 as being f of x, and then the x cubed minus x squared as being g of x. So f of x, I'm just writing back down, and then times the derivative of g, applying power rule. So power rule within product rule here would be 3x squared minus 2x plus the second factor times the derivative of the first, which would actually just be 3. So that's it. You can multiply that out and clean it up a little bit, but that's the derivative. Okay, let's do another one. So g prime, in this case, I'm going to think of x squared as being f of x and sine of x as being g of x. So g prime will be first factor times the derivative of the second. Derivative of sine is cosine. That's something you have to have memorized. Plus the second factor times the derivative of the first would be times 2x. So just to clean this up a little bit, that would be g prime. And then quotient rule, which remember I have the rule or the little rhyme for. I apologize for my cough. Low D high minus high D low, all over low low. So you can either think of this as f of x over g of x, or as high over low. Okay, so dy over dx will be low, d high be 10x minus low d high minus high d low would be just times 3 all over low low. Okay, and that's it. You can simplify. So like if we distributed that 10x, we would have 30x squared minus 20x minus 15x squared combining like terms. That looks a little bit nicer. Okay, and then for h of x, sine over cosine, which you guys know what sine over cosine is, right? It's tangent, and that's one of the rules I told you you just have to have memorized. But this is actually deriving that rule, so if you were to forget it for some reason. So h prime below d high minus high d low would be negative sine x, right? Derivative of cosine is negative sine, all over low low. Well, if we simplify the numerator, that's cosine squared plus sine squared, which there's probably light bulbs going off. Cosine squared plus sine squared is Pythagorean identity 1. So then that's 1 over cosine squared, which would be, since 1 over cosine is secant, 1 over cosine squared is actually secant squared, which is the same as secant times secant, or secant squared written like that. Okay, chain rule. Chain rule. Derivative of the outside, leave the inside alone, times the derivative of the inside. So for this first function here, the x, or the third power is going to be the outside function, and then x squared minus 4 is going to be the inside function. So to the third power is f, and then x squared minus 4 is g. So to find dy over dx, derivative of the outside, I'd bring the 3 down, subtract 1 from the exponent. That part's done. Leave the inside alone, and then times the derivative of the inside would be 2x. So applying power rule to the inside. And we're done. So you could write that as 6x times x squared minus 4 to the second power. Now, anytime you are taking the derivative of a trig function and the argument is something other than just x, then you need to think chain rule. So tan is the outside function, 3x is the inside function. So g prime will be derivative of the outside, which derivative of tangent is secant squared. Leave the inside alone, and then times the derivative of the inside would just be times 3 in this case. So this is 3 times secant squared of 3x. Now this function, f of t, will require a couple different rules, actually a few different rules in order to find the derivative. So we can think of this as a function times a function, right? F times g. But notice that when we go to find the derivative of cosine of 2t, we'll have to think outside function and inside function. Okay, so thinking product rule first, right? Because we have f and we have g. So that would be f prime of t is first factor. And then now to find the derivative of g, we have to think chain rule. So that would be, I'm going to put it in grouping symbols, negative sine, because the derivative of cosine is negative sine. So that's the derivative of the outside, leave the inside alone, and then times the derivative of the inside, close bracket. And then plus second factor, now I'm thinking about finishing product rule, times the derivative of the first. And then this can just get cleaned up a little bit. So minus 2t squared, sine of 2t, plus 2t times cosine of 2t. Okay, this one will also involve applying a few different rules. So if we think of this as a product, so f times g, so finding dy over dx, first factor times the derivative of the second factor. Now, to find the derivative of this second factor, we have outside function, and then we have inside function. Derivative of natural log is one of those I gave you the formula for. Derivative of natural log is 1 over x. So thinking about chain rule, that would be 1 over something. And the something that is leaving the inside alone, so x squared minus 9 times the derivative of the inside would be times 2x. So this was applying chain rule. And then plus derivative of e to the x is e to the x. And then times natural log of x squared minus 9. So that can just get cleaned up a little bit. And that's it. Okay, so that's it for part 1, derivatives and differentiation.